Okay, welcome back. So in this video, we will now be talking about variability. And so previously we've talked about central tendency, things like the mean, median, and the mode. And importantly, when we talk about things like the mean, that alone doesn't always accurately represent our data. As we already discussed, sometimes skew can affect our interpretation of the mean or what the mean sort of conveys or communicates about a distribution. But even in cases where distributions have the same mean, they can also still look very different, depending on their variance. And so variance is a term that we'll define in this video. So for now, I'm throwing this at you, recognizing that we haven't defined it yet. But point here is simply just that these two distributions have very different variances or different spreads. And so, for example, the red distribution here, the tall peak, it has the same mean, but a variance of 100 compared to the blue distribution with the same mean, but a much, much higher variance, right? And so the point is just making the case for the fact that we need to consider other things about distributions besides central tendency, such as in this case, their spread, or in this case, like quite literally, the spread of the data across the distribution. And so the different ways we assess, conceptualize, measure that are different measures of variability, right? So variability meaning that dispersion or spread of data in a distribution. And so generally when we talk about variability, the numbers we'll use for these different measures are positive numbers, right? That could be 0, meaning that there's no variability, in which case it'd just be a straight line. And they can range all the way up to infinity, or more realistically, just however large the data could be. Variance can honestly get really high, like you just saw on the previous slide. The variance was 2,500 for one distribution. But point here is that they cannot be negative numbers, right? They must be positive numbers. Yeah, something with a negative variance would be like a wormhole or something, which goes way beyond what we're going to talk about in this class. That's above my pay grade. So some examples of simple measures of variability are things like the range and the mid-range. So range, something you've probably come across before. Basically here we're just looking at the difference between the largest and smallest value in a data set. Or we could depict that in an equation as L minus S. So a simple example is if we have this data set 1, 2, 3, 4, 5, what's the range? You could do this math probably in your head or on paper. 5 minus 1 is 4, right? So our data were dispersed across 4 different values. And then this one here, 2, 4, 6, 8, 100. 100 minus 2 is 98. But here we can quickly see that, once again, this number alone isn't telling us much about the shape of that distribution. We're just talking about the span. So here, most of our numbers are closer to one end, and then there's just one really high number. But our range is still going to be very, very broad as a result. And so if we just talk about this in terms of the range, we're missing the fact that much of these numbers we're here hovering on the left side of the distribution, or the lower side, right? So again, one number that can tell us something, but not everything. One term that I'd like to at least define, or a few terms, I guess, are fractiles. And so these are different ways to divide data sets into 2 or more equal parts. And so one we've already come across is the median, right? That measure of central tendency that basically splits the data in half. But there are other terms you might come across as well, like quartiles are splitting the data into 4 parts, deciles into 10 parts, and percentiles into 100 parts, right? So that's where the term percentile comes from. Like if I remember taking standardized tests back in the day, and they'd say, oh, you placed in the, I don't know, 68th percentile or something like that. That's just an example of a fractile, of which the median is 1. And so a very basic example of how to locate quartiles besides the median. So previously we talked about how to do this, so you can revisit that. Really, to find the smaller deciles, or fractiles rather, sorry, I had to check my terminology. They're all starting to blur together now that I'm saying them all at once. In order to find, for example, quartiles, we would start with the median for the data. We can label that as Q2 here. And then basically we use that and just continue finding smaller and smaller medians within the different parts. parts. So here our median, once we find that, we have 2 equal parts. Then we can find the lower quartile by finding the median of the lower half. And then to find the upper quartile, we're just finding the median of the upper half, right? And theoretically, we could continue repeating that if we wanted to for smaller fractals. One reason we might find quartiles specifically, say we have data with a extreme number of outliers, right? So some really low, some really high. We might look at something called the interquartile range, which is essentially the 75th to 25th percentile or vice versa. And as you can see visually here, just kind of trimming the data to look solely at the mid portion and ignoring outliers. That's not something we should do casually because there's all sorts of other implications if we ignore outliers. So this is something we shouldn't do without really considering the full context and without really understanding the consequences of doing that or the connotations, but something to mention nonetheless. And so getting to sort of the meat and potatoes of this lecture, variance is a term that we will come across a lot. And honestly, when I talk about variability, I use the term variance because to me, that's just kind of blurred together in my head. They're not synonymous, but I apologize in advance for inevitably when I use them synonymously. So variance is a basic way to measure dispersion of scores from their mean. Yeah, this jargony long definition. Variance is a measure of variability for the average square distance that scores deviate from their mean. That's a lot to digest. So I'll have some visuals here that hopefully will depict exactly what variance is and exactly what standard deviation is, another term we'll come across here in a few minutes. And so variance, similar to what we just previously discussed, variance can be any sort of positive number. Can't be zero, or I'm sorry, it can be zero, which means no variability. It can't be less than zero though, because again, we can't have something with negative variability. So it could be zero or greater than zero. Negative is meaningless. And this is generally a preferred measure because it considers all the scores when we calculate it. Like for example, when we looked at range, we were only looking at the largest and smallest. And so that really isn't telling us much. It's telling us, if you think of this distribution as images we've previously seen of like these mounds, right? Range is only telling us where the ends of the mound is, or of the mountain range, so to speak. Variance is telling us more about what the overall shape of that mound or mountain range looks like. And so some formulas to calculate this. Yeah, there's a lot to take in here. So we'll break this down. Generally, there are 2 primary steps. First is calculating the numerator, which will give us something called sum of squares, which you can see here, sigma sum of squares, right? These things squared. And then we divide that numerator, that sum of squares, divide that by the denominator. And so this varies if we're looking at population or sample variance, just like with most statistics, if we're looking at the population or the sample, that will affect the formula and calculations we use. So let's look at sample variance in an example here. So I want you to imagine that you are a TA for this class, right? You took it already, you passed with flying colors, you're relieved that it's behind you, and now you're going to TA for Site 250. And students completed a quiz, and you recorded the scores in the table at the right? So there's a maximum of 10 points possible. We have 7 students. Evidently, it's a small class. We can see our scores here. Looks like the range is 5 to 10. And I, being a lazy and onerous teacher, I ask you to calculate the mean, the variance, and the standard deviations of their quiz scores. And so first, let's go to our equation and calculate the numerator. And specifically, let's use the formulas for sample variance because we're just focused on this sample. And so to visually depict what we're doing when we calculate a sum of squares, let's first chart out their scores. Right, so we have 7 students and the range of possible quiz values. Student 1 received a 6, student 2 got a 10, and so on and so forth. Right, so we can chart all these numbers out. 6, 10, 5, 9, 7, 10, and 9. First, let's calculate the mean here. That one's pretty easy. So we add them all up, divided by 7, we get a score of 8. And let's go ahead and draw that line on our chart here. So our mean is 8. And so if we look at this, calculating a sum of squares, essentially this value in parentheses, x minus m, that represents a difference between the x, or these individual values, and the mean, which is represented by a line. And so to graphically depict that value right there, that's what we call a deviation. That can be represented by a line from the value to the mean. And the length of that line then represents the deviation or distance of any given value from the overall mean of scores in the sample. And so we can go ahead and visually depict that here with these lines, right? And so we've done all that. And so this is representing, if we just ignore the square for a second to conceptualize this, then the sum of these deviations is represented right here, right? And so 6 minus 8 is -2, right? And so -2 represents the deviation of this x value from the overall mean. 10 minus 8 is 2. We can see here it's 2 above. 5 minus 8 is -3. We can see here it's 3 below, right? And so these numbers simply represent the length of the line, or in other words, the numbers represent the deviation of these numbers from their mean, right? So we can see here we're starting to see something that might make us think about spread, right? How far away these values are from the mean. And so we can, further reduce our calculations here. If we do that, we'll end up with a number of 0, which is exactly why we need to square things, right? If we're just looking at deviations alone, then our calculations aren't going to lead us anywhere because they'll negate themselves, right? They'll end up at 0. Which we don't need to get into why. If you think about it and spend some time with it, I think you'll see why. But so that's why we use squares, right? Because squares will help us get a non-zero solution, or a non-zero way to analyze this variance more closely. And so when we square things, we're literally just creating a square. And it's funny, I showed this to a friend recently, and I could see it click for the first time of why we use the term square. And yeah, so to show you that graphic again here. Nope, whoops. Yeah, so we have our lines. Like if we look at this one, now it's just turning into a square. And so that's what we're doing with all these numbers when we square them. So now we're squaring the deviations to create more of a, I guess here it's 2-dimensional, but I like to say like more of a 3-dimensional space to represent spread. And so now if we do that, we have 6 minus 8, which is 2 squared, creating this square, so on and so forth for all the rest of them. And if we further reduce that, we'll end up with a value of 24. All right, and so that is the sum of squares. That is the numerator in this equation. The sum of the squares of the deviations, or the sum of the squared deviations. And so, so to visually depict this right now, wow, I'm sorry, I'm stumbling over my words, but point being, watch what happens. Okay, there you have it. And so that's what we mean when we say that we are calculating the sum of squares, and that this is representing some sort of variance, or it's helping us to understand variance. Right, we're taking these deviations, squaring them, and that value will form our numerator in the equation for variability. And so to put that on a table of calculating the numerator, because this is something you'll do in the exercises, I like to add the score, the x, the mean, and then the square to make sure I don't mix things up or mess things up. So 6 minus 8, 6 minus 8 squared is 4. And so you can repeat this for all of these to calculate the numbers by hand. And then once again, we do all that, and then we get a value of 24. Right, so this is a by hand way of doing what I just visually depicted on the previous slides. And so we've done that. Now we need to divide by the denominator. And so for the sake of example, let's just plug it in real basically before I visually show you what we're doing here. So if we do this, our sum of squares divided by n minus 1, our n here was it 7, I believe? Yeah, and so our sum of squares was 24 divided by 6, which ultimately equals 4. Okay, so to visually explain what we're doing when we calculate this. So if we calculated our sum of squares previously, now that's going to become the numerator in this formula. And essentially what we're doing is we are calculating, remember our answer was 4, we're essentially calculating the average square distance that scores deviate from their mean, right? Because each of these squares represents a squared deviation. And so this value then, the variance, represents the average squared deviation, right? And yeah, and so we already went over this, but once again, to demonstrate why we square the deviations instead of just using unsquared values. If we do, then we'll just end up with a value of 0. And so that's why we square things, because the sum of different scores, the sum of the differences of scores from their mean is 0. Squaring deviations, by doing that, we get a positive non-zero solution with minimal error. And then after we calculate the variance, we can just correct back, right? So if we squared everything to calculate the variance, we can take the square root, do the inverse, and that will give us the standard deviation, right? So hopefully these terms are starting to come together here. So standard deviation is another statistical term you'll hear a lot. And this is a measure of the average distance that scores deviate from their mean, right? Variance was the average squared distance. Standard deviation is just the average distance. So another term here is the root mean square deviation. Yeah, we could break this word down. You can spend time with it if you'd like. I won't refer to it that way, though. I'll just usually say standard deviation. And to calculate this, we just take the square root of the variance quite basically. So some formulas here. So you can see here we have, I think this is, oh gosh, is this rho? I always mix this one up. Or omega, no. Yeah, I should have looked it up before this video. I apologize. This symbol, I'll clarify in the future. This symbol represents the square root of variance, or the square root of sum of squares divided by n. Or for the sample, s equals the square root of s squared, which equals the square root of sums of squares divided by n minus 1. So basically, we took the previous formula for variance, and we're just adding a square root to it. And so to again visually depict this, so previously we calculated variance, and we determined that this is essentially the average squared distance. Now we need to take the square root of this to get our standard deviation. And so essentially what we're doing is we're taking the square root, which essentially is the length of one of these sides, which is 2. Right? And so if we pull that out, 2, right, the length of that line represents the length of the side of this square, which represents the average distance that scores deviate from their mean. And once again, to give a visual depiction for that, let's go back to our table from earlier with our squares, and let's go ahead and get rid of the squares, get rid of the average, pull those down, and now we see that that is the average deviation, right? Or that's what the standard deviation represents, the average distance. Let's watch that one more time. There you have it. So I would like to give credit where credit is due. I created these visualizations myself, but I got the ideas for it and developed them with, yeah, essentially by using a model that was depicted at this website, which I encourage you to check out. Hopefully these were helpful. We'll go ahead and stop there and see you next time.